Welcome to Operating Systems Unit 12, Part 1. Today we're going to talk about paging techniques and the structure of a page table. So here is the paging example. On the left you have the logical or virtual representation of a process. This is one process. This one process has 8 pages. That means that the operating system has broken up the physical memory, which you look on the right side, into equal size pieces called frames, and then each process gets broken up into logical memory or virtual memory into pages that are the same size as the frames. So you will not have any external fragmentation with paging because there won't be any allocated memory. But what you could have is you could have pages that are smaller than the frames, and that would be internal fragmentation because you can't free up that memory for another process. So if your page is smaller than the frame, then you have internal fragmentation, you have unallocated memory. So each process has a page table associated with it. So if this process has 8 pages, it's going to have a page table that has 8 frames in it, that has 8 entries in it. And the page table stores a lot of information, but the first most important information is it stores what frame the page is in. So as your process starts to execute and it gets loaded and you have these pages and you need to start doing instructions, then your operating system will need to load pages into memory. So as it starts, say for example, you need page 0. So your operating system will then check its free frame list and say, oh, let's find the first free frame or a free frame that I have available, which is going to be frame 1, and I'm going to put page 0 into frame 1, and then I'm going to put an entry into the page table that says that page 0 is in frame 1. So anytime I need to reference an instruction that happens to be on page 0, I can reference it physically for real in memory on frame 1. Now your process is executing and you need page 2. So your operating system checks, is page 2 and checks the page table. Nope, page 2 is not in a frame. Goes and finds a free frame, puts page 2 into a frame, then puts an entry into the page table that page 2 is in frame 3. And so on. Then you need page 1, so I find a free frame. And if the page is not in a frame, that's called a page fault, and we will be discussing that as well. So now I put page 1 into frame 4 and I put an entry in the page table, and now I need page 3. So I find is page 3 in a frame? No, it's not. I have a page fault. I find a free frame. I put page 3 into that frame, and then I put an entry into the page table that page 3 is in frame 7. So that's an example of how paging works. And segmentation works similarly, only instead of having your memory all the same size frames, you have to locate holes in memory to put the segments into, and then this segmentation table is not going to have frame numbers in it, it's going to have base and limits. Base is the location where it starts in memory, and limit is the size. In paging, you don't need a limit because the limit is the same, all the frames and all the pages are the same size. So there are some issues about paging. One issue is that for each process, this is a small example, but a process could have tons of pages, so you need to have an entry for each page in your page table, and your page table must also be in memory. So there's a lot of memory access. In addition, when your operating system actually needs to make a memory reference, if the page is not in a frame, it's going to have a page fault, and if the page is in a frame, it's going to have to make 2 memory references, because if it has to reference memory to reference the page table to find out what page it's in, and then it needs to actually make the real memory reference to reference the page itself. So we're going to talk about that and how a cache can be used to speed that process. In addition, if your pages are too big, you could have issues because then you're taking up way too much memory and using large pages and only using very a small amount of the page at a time, so you're just allocating way too much memory. But if your pages are too small, you're going to have way too many entries into your page table. So again, there has to be issues. There are issues with everything and considerations about how to set up paging. And searching through the page table could take a long time. So let's talk about page frame pairs and caching the page frame pairs. So there's a thing called a TLB, or a translation look-aside buffer, which is a cache where you cache page frame pairs. Now, like I said before, an actual memory access, say for example, you access memory and it takes 100 nanoseconds. But in reality, it's going to take 200 nanoseconds. Assuming there's no page fault and the page is in a frame, it will take 200 nanoseconds because it will take 100 nanoseconds to check the page table and then another 100 nanoseconds to actually do your memory reference. So it's 100% overhead for paging. So say for example you have a TLB and it only takes 20 nanoseconds to reference your TLB, then it would only take 120 nanoseconds to do a memory reference as opposed to 220 nanoseconds. So you can calculate what's called effective access time. So say for example you have an 80% hit ratio. That means that 80% of the time your page frame pair is in the TLB and 20% of the time your page frame pair is not in the TLB. So if you take a look at this math here, it's very simple math. It takes 120 nanoseconds for a TLB hit, and it takes 220 nanoseconds for a TLB miss. So you might say, why is that 220? Well, because it takes 100 to check the page table, it's not there. I mean, 20 to check the TLB, it's not there. Then 100 to check the page table, it is there, and then 100 to do your memory reference. So when you have a TLB hit, it only takes the 20 for the TLB and the 100 for the memory reference. When you have a TLB miss, it takes the 20 for the TLB, the 100 for the page table, and the 100 for the memory reference. So you can do a calculation where if you have an 80% hit ratio, you only have 40% overhead, which is an improvement over the 100% overhead. And if you have a 98% hit ratio, you have only a 22% overhead. So the TLB, this caching is very commonly used, and again, like we've said with all caching, it's due to the fact that page frame pairs, there's a chance that if they've been referenced, they will again in the near future. So the next thing we're going to talk about is address translation, and that you have a logical address and you have a physical address, and we will be talking about that in the next video. Thank you.